Hello. In this video, I will explain normal probability distribution, and here are the objective or materials rather that I will cover in this video. Yeah, you can read these later on. Right, let's start with definition. What is normal distribution? It is a probability distribution where the mean, median, and mode are at the center of the spread. Yes, so as you can see here, the mean, median, and mode is at the middle, and they all have the same value. Yeah, and the curve of a normal distribution is uh, following a bell shape, a symmetrical bell shape. Yeah. So here are uh, some sets of data that come from height of people, uh, IQ scores, scores in an exam, and lifetime of a battery. Um, how do we know whether any of these is following a normal distribution or normally distributed? Well, as mentioned before, to know whether these follows a normal distribution, it must have mean, median, and mode of equal value, and a distribution of a symmetrical bell shape. So let's take height of people as an example. By the way, you can generate this histogram, yeah, using Excel or TI Inspire. And before I go further, just to remind you, normal distribution uh, is unlike binomial. It is meant for continuous data. Yeah, so it is not for a discrete data. Yeah, that's why we use histogram here. As you notice, there are no gaps. Yeah, right. So we have the distribution of the women height. Yeah, the blue, the purple curve. Sorry, and the blue curve belongs to the men height distribution. As you can see, both follows a symmetrical bell shape. That also means uh, the mean, median, and mode are of the same values. Yeah, so height of people is normally distributed. Okay, so having said that, the normal distribution is a descriptive model that describes real world situation under this function here. And let's not worry about this function for the moment. Why is that? Because as you can see in the syllabus shown at the beginning, you will be using, or you must use, calculator to find the probability of a normal distribution. So you don't really have to worry much about this function. Right, carry on. Let's go through some properties of a normal distribution. Okay, number one, the mean, median, and mode are equal, as mentioned just now. Yeah. Number two, again, as mentioned before, the normal curve is bell-shaped and symmetric about the mean, yeah, or mode and median as well, because they're of equal value. Yeah. Number three, the total area under the curve is equal to 1. So the area under this bell curve, yeah, the yellow color, is equal to 1, yeah, because the probability is equal to 1. Okay, next one, the normal curve approaches but never touches the x-axis as it extends further and further away from the mean. As you can see here, the curve, as it extends further away from the mean, remember mu is the mean, and this curve is going away, this curve will never touches the x-axis, only approaching. Similarly to the curve on this right hand side, as it extends further away from mu or mean, it will never touches the x-axis, only approaching the x-axis. Okay, the fifth one, so now this is rather long. Please don't be confused. Let me display the axis. Okay, number 5, between mu minus sigma, remember mu is the mean, sigma is the standard deviation, yeah? So between mu minus sigma and mu plus sigma, the curve, this curve here, opens downward or concave down, yeah? Between mu minus sigma and mu plus sigma, the curve opens downward or curve downward. The graph curve upward to the left of mu minus sigma, this one here, to the left of mu minus sigma, this part, the curve opens upward. Yeah. Similarly to the side here. Yeah. The curve to the right of mu plus sigma, the curve opens upward. Yeah. And these 2 points, yeah, the point in between the curve opening up and the curve opening down is called the inflection point. Yeah, so if there's a change in the opening, concave up, concave down, and the point in between, such as this one here and that one there, is called the inflection points. Okay. Moving on to the means and standard deviation. A normal distribution can have any mean and any positive standard deviation. Okay, let's take a look at some examples. Okay, right. This curve here has a mean of 3.5, and standard deviation sigma is approximately equal to 1.3, whereas this curve here, or this distribution here, has a mean of 6, and standard deviation is approximately equal to 1.9. So any normal distribution can have any mean and any positive standard deviation. Right, take a look at this example. Given curve A and curve B, which one has the greater mean and which one has the greater standard deviation? Well, the line of symmetry of curve A, this is the line of symmetry, occurs at x is equal to 5. Yeah. Remember, the bell curve for normal distribution must be symmetrical, and the line of symmetry passes through the mean. Yeah. The line of symmetry of curve A occurs at x is equal to 5, and the line of symmetry of curve B occurs at x is equal to 9. Curve B has the greater mean, obviously, and curve B is also more spread out than curve A, so curve B has the greater standard deviation. All right, so this is very important for you to remember and to understand. No matter what mu and sigma are, or no matter what mean and standard deviation are, the area between mu minus sigma and mu plus sigma is about 68%. So let me generate the curve. Okay, so the area between mu minus sigma and mu plus sigma, okay, this part here, is about 68%. Yeah, right? Remember the total area under the curve is 1 or 100%, yeah? And next, the area between mu minus 2 sigma, this one here, mu minus 2 sigma and mu plus 2 sigma is about 95%. Yeah. And lastly, the area between mu minus 3 sigma and mu plus 3 sigma is about 99.7. So the area under the curve, yeah, is equal to 99.7%. And almost all values fall within 3 standard deviation. Remember, this is also called 68, 95, 99.7 rule. Okay, let's go through this example. Okay, let me generate the curve first. There you go. Here, given the mean life of a tire is 30,000 kilometers, so let's put the mean at the middle. And given the standard deviation is 2,000 kilometers. Question A. 68% of all tires will have a life between what kilometers and what kilometers? Well, remember the 68, 95, and 99.7 rule before in the slide shown to you previously. So 68% should be between, okay, let me just write here, should be between mu minus sigma and mu plus sigma. And we know that mu is equal to 30,000. So that's 30,000 subtracted by standard deviation is 2,000. Okay, and over this side is 30,000 plus 2,000. Okay, so we have 28,000 and 32,000. So that is the answer. Yeah, because this is the area that we want. Yeah, 68%. Yeah, the area under this curve is between 28,000 and 32,000. Okay, next one B. 95% of all tires will have a life between what value, what kilometers rather, and what kilometers. Okay, now this is the area under the curve, which is equal to 95%. Yeah, which is, let me just clear this up first, which is mu plus, oh sorry, it's supposed to be minus 2 sigma and mu plus 2 sigma. We know that the mu is equal to, again, 30,000. So I just put mu 30,000 subtracted by 2 times the standard deviation, in this case 2,000, and this one is plus 2 times 2,000. Alright, so we have 26,000 over here, and over this end we have 34,000. Yeah, so there we go. Yeah, and what percent of the tires will have a life that exceeds 26,000? Well, this is 26,000. Yeah, and the question is asking what percent. Yeah, what percentage of the area under this curve will have a life that exceeds 26,000? So this area here, anything after this line. Yeah. We know that the normal distribution is having a symmetrical bell shape. So this half is equal to 50%. Yeah, the area of this half here. This is 50% plus 34% plus 13.5%. So that's equal to 97.5%. Yeah, the area which is representing the tire life that exceeds 26,000 kilometers. Next one, if a company purchased 2,000 tires, how many tires would you expect to last more than 28,000? Yeah, how many tires would you expect to last more than 28,000? So easy, just like question C. The area of this half here, half of the curve, is 50%. So the area of this we know, which is 34%. So we have 34% plus 50% equals to 84%. So this is an example of the 68, 95, and 99.7 rule. Okay, so we have 84%, this 0.84, multiplied by 2,000. That's equal to 1,680 tires that the company can expect to last more than 28,000 kilometers. Yeah. Let's continue to the next example. Here, given the speeds of cars on the highway have a mean of 95 kilometers per hour with a standard deviation of 5 kilometers per hour. What percentage of cars average less than 85 kilometers per hour? Okay, let's generate the number line and the normal curve. Right, so this is 95, which is the mean, and 85 is over here, minus 2 standard deviation away from the mean. Okay, this is the relevant position. Okay, and the question is asking for the percentage of cars average less than 85. So less than 85. So this is actually 85. This because this is the mean. Yeah, this is the mean. This is minus 1 standard deviation away, and this is minus 2 standard deviation away. Now this is what we want. Yeah, but this is equal to 85 kilometers per hour. So the percentage is equal to 2.35% plus 0.15%. Okay. Next one, question B. If a police car stopped cars that were going more than 105 kilometers per hour, how many cars would they stop? If there were 8,000 cars on the highway, so more than 105, so this one here. Yep, this is 2 plus 2 standard deviation away from the mean. So this is what we want, more than 105 or going faster than 105. So that means 2.35% plus 0.15%. Yeah, because this line here, this is plus 2 standard deviation away from the mean. So that is equal to 2.5% multiplied by 8,000, so 200 cars. You notice that this is symmetrical. Therefore, this area or percentage is just equal to this area or percentage. Yeah? Okay, moving on to the next example. A grading scale is set up for 1,000 students' test scores. It is assumed that the scores are normally distributed with a mean score of 75 and a standard deviation of 15. Okay, question A. How many students will have scores between 45 and 75. Let me open the whiteboard. Okay, the mean is 75. 75. And question A asks for how many students will have scores between 45 and 75. Well, 45 means 75 minus 30, so that's 2 standard deviation away. Sorry, that should be 15. 2 standard deviation away from the mean. Okay, that's equal to 45. So that should be located over here. So the question wants the number of students between 45, yeah, minus 2 standard deviation away from the mean, and 75, which is the mean itself. So the question is asking for this part here, which is equal to 13.5% plus 34%, which is equal to 47.5%. Okay. Okay, now let's continue to the next example. A grading scale is set up for 1,000 students' test scores. It is assumed that the scores are normally distributed with a mean score of 75 and standard deviation of 15. Okay, let's generate the normal curve. Okay, that one there. So the mean is 75, and question A is asking for how many students will have scores between 45 and 75. So between 45, which is minus 2 standard deviation away from the mean, yeah? So between 45 and 75, so that's just equal to 13.5% plus 34%, which is equal to 47.5%. Next question B, if 60 is the lowest passing score, 60 is the lowest passing score, how many students are expected to pass the test? So the students must score 60 points or above, yeah? So the area under the curve is equal to 50% plus 34%, which is equal to 84%, or 0.84 multiplied by the number of students, which is 1,000. Then that's equal to 840 students. Okay, let's go through some notation. Almost similar to the binomial distribution notation. This uppercase X means the random variable X is normally distributed, yeah, that uppercase N is normally distributed with a mean of mu and a variance of sigma square, yeah. So note the variance is often written as the standard deviation squared, yeah. Okay, let's just go through this simple example to make sure you understand the notation. Write down the mean and standard deviation of each of the following normal distribution. And second one is the mean is equal to 85. Standard deviation is equal to square root of 36, which is 6. Then last one, the mean is equal to 0 and standard deviation is equal to 1. Yeah, square root of 1 is just 1. Okay, now moving on to the probability and normal distribution. If a random variable x is normally distributed, you can find the probability that x will fall in a given interval. by calculating the area under the normal curve for that interval. Okay, so this is the normal curve. Okay, and the statement say you can find the probability that x, random variable x, will fall in a given interval. That means x interval, by calculating the area under the normal curve. So for example, uh, this shaded part represent the probability of x is less than 15. And remember, probabilities and values of the variable must be found using technology or calculator. So we will not do this manually. Okay, let me open the TI. Here we go. So to calculate the probability of x is less than 15, okay, we use normal distribution. So add calculator, and then we go to menu, probability, distribution. Now we use normal CDF, yeah, since this is continuous data we are dealing with in normal distribution, so we always use normal CDF. Okay, so the upper bound is very obvious, 15. Okay. What about the lower bound? Well, you can put any small values. A correction to what I said just now, since this curve, yeah, this part of this curve is heading toward a negative direction, so what we need as the lower boundaries is a large negative numbers because it is heading toward infinity. So we need a very large negative numbers. By default, your TI has this number here, which is minus 9 multiplied by E. E means 10 to the power of, yeah, in this case 999, yeah, and we know the mean and the standard deviation, so we can calculate the probability, yeah, which is 0.841, okay, which is equal to the area shaded. Okay, let's move on to this example. The average on a statistics test was 78 with a standard deviation of 8. If the test scores are normally distributed, find the probability that a student receive a test score greater than 85. Yeah, sorry for this. Okay. Um, you don't need to sketch this normal distribution curve, yeah, but often it helps. But if you know the situation, I mean, you understand the problems without having sketching it, and you calculate it directly, that's fine. Yeah. So this is the normal distribution curve. The mean is given 78. Standard deviation is 8. Yeah. And the question is asking, find the probability, which is the area under the curve. Find the probability that the student receive a test score greater than 85. Okay, let's use calculator for this. We go to menu, probability, distribution, normal CDF. The upper bound can be any large values, yeah, because remember this curve continues without touching the x-axis. So we can put large numbers like so. Any large numbers will do. The mean is given, which is 78. Standard deviation 8. Click OK. There you go. That is the probability or the area under the curve. Yeah, 0.191. So the probability of x greater than 85, yeah, this one here, the student receive a test score greater than 85 is equal to 0.191. Okay, very simple. Let's continue to this example here. We now know how to use a calculator, hopefully, to calculate the probability, but we are also required to do the reverse. Meaning, given a probability of being in a region, how do we find the value of the boundary? Yeah, so we want the boundaries now. Previously, we are given the boundaries, the upper and lower boundaries, and now we are not given those boundaries. Okay, here, random variable x is normally distributed with mean 20 and standard deviation 3. Find correct to two decimal places the values of a such that probability of x less than a is equal to 0.75. Right, well, here is the instruction. Okay, well, let's just do that in calculator. So we have menu, probability, distribution. Now this time you go to inverse normal, yeah, because in this case we are given the probability or the area under the curve, but we don't know the values of a, the boundaries. We don't know the boundary. So we click inverse normal or inverse norm. The area is this one here, 0.75. That's given, yeah, 0.75. The mean is 20. It's from here, 20. The standard deviation is 3. Then click OK. So that is the value of A, the value of A or the boundaries, that one there. Yeah, and the question says find A correct to two decimal places. So that's just equal to 22.02. Okay. Okay, now let's move on to question B. Here is given probability of x is greater than a is equal to 0.4. So the area under the curve or the probability is given 0.4. Notice this notation, x is greater than a. So let's just make the sketch. Okay, so if this is the boundary a, yeah, x is greater than a is 0.4. Therefore, this shaded area has to be 0.6. Remember the calculator, when we do the inverse normal, only recognize the area to the left of the boundaries. So if we are given 0.4, which is the area for x greater than a, 0.4, we need to find this area here, the area where x is less than a. Yeah, again, the calculator only recognizes the area to the left of the boundaries. So let's calculate. We go to menu, probability. Sorry, let me move this closer. Okay, distribution, inverse normal. So the area that we are using is again 0.6, not 0.4, yeah, 0.6. 0.6. The mean is 20, standard deviation is 3. So we click OK. So that's the answer, 20. Question C. Given probability of 16 is less than x, x is less than a is equal to 0.3. Well, let's generate the sketch. So between 16 and a, the probability of the area is 0.3. Find this boundary here. Okay. So first thing first, we need to find this red area, yeah, where the probability of x is less than 16, that one there. Okay, we need to find that area, which is 0.09121. Okay. Oops, sorry. Yes, this one here. If you use calculator like before, yeah, we can find the value of this area and we add 0.3, yeah, to that area. So we know the entire area to the left of A. And then we can use inverse norm because the calculator cannot find the inverse normal of that particular segment. If you remember, if you do inverse norm, okay, probability distribution inverse normal, the area has no boundaries. I mean, there's no lower upper boundaries. Yeah, here's only area. So that's the reason why you need to find that red area first, add 0.3 to that red area, and then we do the inverse norm to find A of the area of the entire area to the left of A. Okay, so we do inverse norm of 0.39121. That gives you 19.17. Okay, moving on to this context here. Consider the following. A calculus test had an average of 73 with a standard deviation of 8. A Chinese language A test had an average of 87 with a standard deviation of 6. A physics test had an average of 70 with a standard deviation of 15. Recall that standard deviation is a measure of spread. Yeah, it is an average distance of data points away from the mean. So comparing these distribution is like comparing apples to oranges because these are all of different subjects. Yeah. So to make a fair comparison, we need to convert all scores to the same scale, meaning we need to standardize the scores, converting them to the standard normal distribution with a single mean and a single standard deviation. So we need to convert all of these so that they all have the same mean value and the same standard deviation. Okay, and that brings us to the standard normal distribution. So not only normal distribution, this is standard normal distribution, or often called Z distribution. So every normal random variable distribution can be transformed into the standard normal distribution or Z distribution using this formula. So this you need to remember. Z is equal to x minus mu over sigma. Yeah, mu is the mean, sigma is the standard deviation. Yeah, and x is just the value. Okay, what about z? We will go through it later, yeah, as we go along. The z distribution has mean 0 and standard deviation 1. So this is automatic. Mean has to be 0 and standard deviation 1 for the standard normal distribution or z distribution. Yeah. When a set of data values are normally distributed, we can standardize each score by converting it into a z-score. So we convert x, yeah, or score, yeah, each score x can be converted into a z-score, where x represent an element of the data set. So that's the definition for x there. The mean is represented by mu and standard deviation by sigma. What is a z-score? It is a measure of an observation distance from the mean. Yeah? How far it is from the mean. The distance is measured in standard deviation units. If a z-score is 0, then it is on the mean. If a z-score is positive, meaning it is above the mean. If a z-score is negative, then it is below the mean. If a z-score is 1, it means it is one standard deviation above the mean. If a z-score is negative 2, then it means it is 2 standard deviation below the mean. Yeah. Let's take a look at this example here. Remember, z is the number of standard deviation above the mean. If we use IQ distributed as random variable x, yeah, is normally distributed with mean 100 and standard deviation 15. Then to find the z-score, you use this formula. Yeah, z is equal to x minus mu over sigma. If we look at 130, that's equal to 2. Well, that makes sense because the mean is 100. Standard deviation is 15. 130 means it is being 2 standard deviation away from the mean. 2 times 15 is 30. Yeah, 30 plus 100 is 130. So 2 standard deviation away from the mean. And all of these values, yeah, z-score can be calculated. Okay, let's just do one example. Remember the formula to find z-score, or how far the score from the mean. That's equal to x minus mu over sigma. Okay, and let's do 85. Yeah, so x is equal to 85. The mean is 100. Divided by the standard deviation, which is 15. So 85 minus 100 is minus 15 over 15. That's equal to negative 1, which is the same to this. And also 85 is minus 1 standard deviation away, because the mean 100 minus 1 standard deviation away, that's equal to 100 minus, minus 1 multiplied by, standard deviation is 15, so that's equal to 80. If the IQ, so if the IQ score, or if x is equal to 85, it means minus 1 standard deviation away from the mean, 100. So that's the meaning of z-score. Yeah, how far away is the score, or x, yeah, is from the mean. Okay, then why do we use z-score? Again, as before, z-score make it easier to compare scores from distribution using different scales. For example, if there are two tests, yeah, and one student, Fred, scores 78 in test A, with mean score 70 and standard deviation 8, and in test B, Fred scores 78, uh, and the mean score is equal to 66, and standard deviation is equal to 6. Did Fred do better or worse on the second test? Well, so in conclusion, Fred did much better on test B. Yeah, if we recall the previous uh, normal curve, this one here, on test B, uh, Fred scored 2 standard deviation away, okay, plus 2 standard deviation away. So we can say that he is at the top 2.5%. Yeah, if we look at the area under the curve, 2.35% plus 0.15%. But for test A, this is test A, Fred's score is only 1 standard deviation away. So that one there. Yeah. So again, Fred did much better on test B. If each data value of a normally distributed random variable x is transformed into a z-score, the result will be the standard normal distribution. Yeah? If this is the normal distribution having x score, mean mu, and standard deviation sigma, yeah, they are of some values. Yeah, if it is transformed, yeah, if x score is transformed into a z, then we have a standard normal distribution having a mean 0 and standard deviation 1. Uh, Previously, we used standard normal table to find the area, yeah, under the curve. But of course, we don't do this now. We use the calculator.